Now we want to introduce the idea of electron configurations.
So, electron configurations are descriptions of where electrons are in an atom. And namely, when I say where, it's which orbitals, which subshells, which shells are those electrons in, right? We have all of this distribution, all this description of places to put electrons. Well, where have we put them? And there are a couple different rules that we're going to use to work out kind of where electrons go. They're the Pauli exclusion principle and the Aufbau principle. So we're going to work through those, go up one at a time, and kind of build up how we come up with electron configurations.
So the first one we want to talk about is the Pauli exclusion principle. We actually touched on this in the last set of videos, and the Pauli exclusion principle says that no two electrons in an atom can have the same four quantum numbers. So you have four quantum numbers, n, l, m sub l, and m sub s. There are possibly unique values for each of those, or relationships between those that we talked about. And so if you have a set of four of those, and they have particular unique values, you have fully defined a given electron. So let's take a look at what the implication of this is. So let's look at, say, electrons A, B, and C. And so we could give them all quantum number n equals 3. That would mean that all of those electrons are in the same shell. That's fine. We can even then give them the L. We can say then that L equals 1 for all of these electrons. That would mean all of these electrons are in the same subshell. Okay, so we can have 3 electrons in the same shell, in the same subshell. What about the same orbital, right? That would be specified by the m sub L quantum number. If that value is 0, that would specify which orbital they're in. Okay, but if we then look at the fourth quantum number, m sub s, we know we can have plus 1/2, we can have minus 1/2, and that's it. There are only 2 values of m sub s. So if you can only have in one orbital 2 total electrons, no orbital can have more than 2 electrons. So the important principle, or the important impact of the Pauli exclusion principle, is that each orbital holds up to 2 electrons. You can't have more than that. You can have less than that. An orbital could only have 1, but you can't have more than 2 electrons in an orbital. And so we've looked at kind of some of the effects of this last time. We know that in an S-type subshell, there would be 1 total orbital and 2 total electrons. In a p-type orbital, there are 3 total orbitals and a total then possibility of 6 electrons. D-type orbitals have subshells, have 5 orbitals, 10 total possible electrons. F gives you 7 orbitals and 14 electrons. And that's going to continue on. And it's only based on the type of subshell. So if it's SPDF, it doesn't matter what the number in front of there is. So 1s, 2s, 3s, 4s all have exactly 1 orbital in them and a total max occupancy of 2 electrons. So that gives us our rules for how many kind of electrons we can put into orbitals. So then the question is, how are the electrons going to fill those particular orbitals or occupy certain orbitals? And it's going to be based around the energy of those orbitals. Okay, so we have our orbital energy. We talked a little bit last time about the idea that orbital energies are dependent on just the first 2 quantum numbers, n and l. So in a given subshell, all of the orbitals have the same energy. And the energy ordering is that generally shells, we order by shell, and within a shell, we order by the L quantum number. So S is less than P is less than D is less than F. So we kind of have 1, 2, 3, but then there's a spread around those. And that leads to kind of some interleaving here, where we can see that 3D has a higher energy than 4s. Even though 4s is in a higher shell, it is a lower energy because the s's are more stable. That shape is more stable than d's. This pattern continues. 4d is a higher energy than 5s. Overall, this leads to an ordering of all the different subshells based on energy. So this ordering here is just something you can be given. It just keeps going. You do not need to or want to memorize this. You should always use this as a guide. You should always have, if you're ever working through electron configuration problems, we can always use this ordering here to let us kind of follow through what the subshells are and what their ordering is. So when we're going through a set or all of our different kind of subshells that we have, electrons are going to occupy the lowest energy subshells before they go into high energy subshells. Makes sense, right? Electrons are going to take whatever the lowest energy, whatever's the easiest way to arrange. And so they're going to go into those lowest energy subshells. And you won't put, electrons won't go into higher energy subshells until the lowest energy is full, right? So you basically put all the electrons, fill a subshell, then electrons start to go up into higher energy shells. Another video down. Only one question so far, right? We're halfway through. This is halfway through the set. I think there might be some questions on the back half. I'll see you there.